So we're going to look at the area between curves and then hopefully the mean and RMS values. The main thrust today, though, is to look at this area between the curves and these mean values. The RMS is really just a special case for mean values. So once we've studied that, that will be quite straightforward. So let's look by way as an example of the first example here. So if we have two curves, the blue one and the red one there, and we want to find the area between them, the idea is to find the area underneath the blue curve, this whole area underneath here, and then subtract from that the area underneath the red curve. Before we can do that, though, often we need to know what are these limits, you know, these points here. Where am I integrating in between to find this area? So I need to find these points of intersection and then integrate to find the area. So the first thing to do is find these points of intersection. So what we do is we use the fact that, of course, at these points of intersection, then y and x, whatever they are, satisfy both equations. So we can solve them simultaneously using the method of simultaneous equations to do this. How might we do that? Yep. So we'll get y squared equals x to the 4. Yep. Another way to do it would be to say substitution is another way to do it, because we've actually, if we look at number 1 here, it's saying y equals x squared. So in the second one, instead of y, we can write x squared. And so, using substitution, one into 2, so we substitute 1 into 2. That means instead of y in equation 2, we're going to write x squared. So we write y squared, which is now going to be, x squared equals 8x. And so suddenly we've only got x. X squared squared is x to the 4 using the laws of indices. Try and solve. Now, I'll wait till you get to that point, because the next point's important. At this point, you might be tempted to divide by x. But by dividing by x, you're actually ignoring one possible solution. You're getting rid of a possible solution by dividing by x. If you divide both sides by the unknown, that often leads to that error. So what we do instead is actually just think of this as, solve it in the same way we might solve a quadratic. We get everything over to the left-hand side. So we say x to the 4 minus 8x equals 0. And then we factorize the left-hand side. What does that mean, Mason, to factorize it? Yeah, what's common to both of these terms? Yeah, so I can take x outside the bracket, leaving x cubed minus 8 inside the bracket equals 0. If we look back at this point, if I decided to divide by x, I'd have had x cubed equals 8, or x cubed minus 8 equals 0, which is this bit, in other words. And we would have missed the fact that by factorizing, looking at the fact that this right-hand side is 0 means that one possible answer for x is that x equals 0. Because if x equals 0, it doesn't matter what's inside the bracket, the whole answer is going to be 0. And by dividing by x at this point, we would have missed that solution. So we can state that either x equals 0 or the bracket x cubed minus 8 equals 0. And so one solution is that x equals 0, and the other solution is that x cubed minus 8 equals 0, which implies that x cubed equals 8, adding 8 to both sides. So therefore, or it implies that x is the cube root of 8. X equals 2. So we've got two possible solutions, x equals 0 or x equals 2. Ooh. So now substitute our values for x back in. So x equals 0 is one solution, and which is the easiest equation to use. I would suggest maybe the first one is, because y is just x squared. So y equals x squared, so therefore y equals 0, because 0 squared is still 0. And for x equal to 2, y equals x squared, or 2 squared, which is 4. So therefore y equals 4. So the points of intersection are 0, 0, and 2, 4. Now we can sketch this thing, okay? We can sketch it. We know that if that's 2 and that's 0, we know that it crosses at 0, 0, and 2, 4. And so the curves will look a bit like this, y equals x squared curve, and y squared equals 8x, or y equals the square root of 8x will be this curve here. So now we just need to integrate between the limits of 0 and 2. Yeah. Okay, so now we're going to do the integral. We're going to integrate the top curve, which is y equals x squared, between 0 and 2. So the area is going to be the integral between 0 and 2 of the top one, minus the integral between 0 and 2 of the bottom curve, which is square root of 8x. So we can do that one. That's okay. How are we going to rewrite this one, though, so that we can do it? How are we going to make this easier for ourselves, this integral? I could take the square root of 8 outside the integral. So square root of 8 times the square root of x is the same thing. And so I'm left inside the integral, the square root of x, which using powers I'd write as x to the power a half, right? Yeah. Okay. So that's the way we'd rewrite it. Now I'd perform the integration on it, add 1 to the power, divide by the new power, and then put the limits in. So if I just pause this for a second, you can carry on and do that for me. So we could write it like this, okay? Do each integral and put the limits in. But because we're putting the both limits in, and the both limits are the same, we can actually speed things up for ourselves a little bit. What do you think we can do to speed the process up? I can, because I'm doing this between 0 and 2, and this between 0 and 2, because the limits are the same, I can put the top limit into both of them at the same time, and then the bottom limit to both of them at the same time. So in other words, I can do this. 2 root 8 over 3 x to the 3 over 2 between 0 and 2. I can do it all in one hit like that. So I put both terms inside one set of limits. Okay, all I've done is taken the 2 and the 3 outside with the root 8, so that's 2 root 8 over 3, that's this bit, times x to 3 over 2. And now I can put x equals 2 in, and then x equals 0 in and work it out. Right, Mason? You can work them out separately. but you can also, because they're the same limits, work it out in one hit. It turns out to be negative 2 2/3, so therefore we must have done it the wrong way around. So it's pointing out that, in fact, be careful, if you look at the beginning here, you might have noticed as you're looking at this video that actually it's the area under this curve minus the area under that curve. You'll get the same answer, but it'll be positive rather than negative, which is what we want. Okay? So look at this exercise now. Page 508 in the new text. So what page is it in the old text? Or in the old textbook, page 486. Have a go at that question.